The body is very sensitive to its pH level. Outside the range of pH that is compatible with life, proteins are denatured and digested, and enzymes lose their function in many physiologic processes, such as the maintenance of energy stores, transport of substances across cells, and intracellular signaling systems needed for the body to sustain itself. Our body has a number of mechanisms that prevent pH fluctuations. Some of these prevent minute-to-minute pH fluctuations over the course of the day, whereas others maintain pH balance from day to day. Hydrogen regulation consists of chemical buffering, respiratory regulation, and renal regulation. Respiratory regulation is considered as a physiologic type of buffer, which is 1 to 2 times as great as chemical buffers. Its primary role is the removal of carbon dioxide via alveolar ventilation, stimulated by an increased hydrogen ion concentration. Assuming that the metabolic formation of carbon dioxide is at a constant rate, increasing alveolar ventilation would cause a decrease in carbon dioxide and a decrease in hydrogen ion concentration, therefore increasing the pH. The chemical systems that maintain a normal pH are called buffer systems, preventing the pH from drifting far from normal. Approximately 60 to 70% of the total chemical buffering of the body fluids results from the action of intracellular proteins that have high concentrations and pKs fairly close to 7.4. In the red blood cell, hemoglobin is an important buffer. As for the remaining 30 to 40%, extracellular buffer pairs, bicarbonate, phosphate, and ammonia take over. One of the members of the pair is an acid because it is capable of donating a proton, thus lowering pH. The second member of the pair is a base because it is capable of accepting a proton, thus raising pH. But the major homeostatic control point for maintaining the normal pH in the plasma is renal excretion, which makes use of chemical systems. Now let us travel through the urinary tubules to see how these chemical buffer systems act. The sites of hydrogen secretion are the proximal, distal tubules, and the collecting duct. The different compartments inside the renal tubules are the lumen, which contains a tubular fluid, the apical membrane, which has various channels, the basolateral membrane, with tight junctions and channels, regulating the components of the tubular fluid, transporting them through the interstitial fluid into the peritubular capillaries. The basolateral membrane of the proximal tubule also has an active sodium-potassium pump, which transports 3 sodium ions out for every 2 potassium ions in. This keeps the intracellular sodium low, which sets up the sodium concentration gradient required for the sodium-hydrogen exchanger in the luminal membrane. Hydrogen secretion from cells across the luminal membrane is mostly an exchange for sodium ions, and to a small extent through a proton ATPase. In the proximal tubule, secreted hydrogen react with filtered bicarbonate to form carbonic acid. In the presence of carbonic anhydrase, luminal carbonic acid rapidly dehydrates to carbon dioxide and water, which are rapidly reabsorbed by the cell. Inside the cell, dissociation of water into hydroxide and hydrogen is promoted by hydroxylation of carbon dioxide to generate bicarbonate, leaving the cell through the basolateral membrane in a 3-to-1 co-transport with sodium catalyzed by soluble carbonic anhydrase. Hydrogen is exchanged for sodium ions through a high-capacity isoform of the sodium-hydrogen exchange proteins. The net result is that sodium bicarbonate disappears from the lumen and appears in the blood side of the proximal tubule cell. A similar process occurs in the thick ascending loop of Henle and intercalating cells of the collecting duct. Hydrogen is secreted into the tubular fluid by 2 mechanisms at the intercalated cells of the collecting duct. The first involves an apical membrane hydrogen ATPase. The second mechanism couples the secretion of hydrogen to the reabsorption of potassium via a hydrogen-potassium ATPase. Then bicarbonate exits the cell through the basolateral membrane via a chloride bicarbonate antiporter. Another type of intercalated cell secretes bicarbonate rather than hydrogen, having its hydrogen ATPase at the basolateral membrane and the chloride bicarbonate antiporter at its apical membrane. Normally, the entire filtered load of bicarbonate is reabsorbed, where 80% is reabsorbed at the proximal tubule, 15% at the thick ascending limb, and the remaining 5% at the collecting duct. The proximal reabsorption of bicarbonate can be affected by many factors, including the pH, the carbon dioxide tension levels, the potassium levels, and the extracellular volume status. A decrease in pH, potassium levels, and the extracellular fluid volume will result in increased bicarbonate reabsorption. An increase in carbon dioxide tension will also result in increased rates of bicarbonate reabsorption. Another function of the kidney in acid-base homeostasis is to generate new bicarbonate molecules to replace those consumed in buffering protons, which is done through ammonia and titratable acid excretion, where ammonia excretion is the predominant mechanism through which the kidney increases new bicarbonate generation. But first, let us see how non-bicarbonate buffers act generally. The primary urinary buffer, hydrogen phosphate, and the other buffers, collectively called titratable acids, use the hydrogen ATPase for hydrogen secretion with subsequent hydration of carbon dioxide, producing bicarbonate that is reabsorbed in the blood. In ammonia excretion, we must take note that it requires the integrated activity of several nephron segments. Proximal tubule cells metabolize glutamine to form equimolar amounts of ammonium and bicarbonate. This is the new bicarbonate molecule absorbed into the peritubular capillaries. Ammonium is reabsorbed in the medullary thick ascending loop of Henle and diffuses through the interstitial space to the collecting duct. Ammonia then diffuses into the luminal fluid, where proton secretion by collecting duct cells lead to the formation of ammonium, which remains trapped in the luminal fluid. So in summary, the blood has an optimum pH of 7.35 to 7.45 and is maintained by the lungs and kidneys. Through the respiratory regulation, the lungs can control blood pH through exhalation of carbon dioxide, decreasing blood acidity. However, the more effective means of acid-base balance is through the renal regulation, which is through the secretion of hydrogen ions and using of chemical buffers, such as bicarbonate, phosphate, ammonia, and intracellular proteins to control blood pH. Hydrogen secretion and bicarbonate reabsorption sites include proximal tubules, distal tubules, and the collecting duct. Bicarbonate ions can be produced via ammonia excretion and titratable acid excretion. Ammonia produced or released into the luminal fluid to trap excess hydrogen to control the pH levels of the urine.